Hi Wildcats, this is Unit 9, Focus Question 3 Notes Overview. Focus Question 3 is all about mechanical energy. So if we start by looking at this picture, it says, what observations can we make about the relationship between potential energy and kinetic energy? And I think this is something that a lot of you saw last week, although it wasn't explicitly stated in the notes. The practice problems and even the lab you did show this relationship. So this skier at the top has, it tells us we know they have no kinetic energy, so they must be at rest. And they have some height off the ground, and they give that a value, their potential energy of 50,000 joules. And so what we see as this skier goes down is that their potential energy decreases, which makes sense because they are now at less height, but therefore they're moving because they're going down. And so their kinetic energy increases. Down here, they're lower, again, so they have even less potential energy, but more kinetic energy. And that makes sense. If this skier was going down this hill, we would expect their velocity to increase. And as their velocity increases, since kinetic energy is 1/2 mv squared, as their velocity increases, therefore their kinetic energy does. As they go back up, as their height increases, their potential energy again increases and their kinetic energy goes down. So this person would slow down as they went up in the air. That's something that I think we're familiar with. And then as they come down, now they have no height relative to their initial position, and so all of their energy would be kinetic. And what we see in all of these values is that no matter where they are, their total energy is equal to the same value, which is 50,000 joules. So here, it's 50,000 and it's all potential. Here, they have some potential but also some kinetic, but that's still 50,000. And the same thing is here, here, and here, everywhere. And so this gives us the idea, or this concept of mechanical energy. And mechanical energy is defined as the sum of all the kinetic and all the potential energy an object possesses. For this year, we're just going to look at gravitational potential energy, but just be aware there are other types such as elastic potential energy in like a spring or a rubber band. So we're going to focus just on gravitational, but there are other types. So to talk a little bit about mechanical energy mathematically, if the definition is it's the sum of kinetic and potential energy, we could write that as mechanical energy is equal to kinetic energy plus potential energy. And we know from many other science classes, your previous science classes, that energy can't be created or destroyed. It only changes forms. And so this is a perfect example of that. Potential energy can transfer to kinetic energy and vice versa. So here in this picture, this football has some height off the ground, so it has some potential gravitational potential energy, but it's also in motion, so it has some kinetic energy, and its total mechanical energy is the sum of those. So they give these values: 32 joules of potential energy, 45 joules of kinetic energy, so its total mechanical energy would be 77 joules. We see this is a similar picture to the one we saw on the last slide, where we see their energy changing from one form to another depending on their velocity and also their height relative to the ground. If we look at this picture, we'll stick with our formula. Mechanical energy is kinetic energy plus potential energy. So now let's put some numbers on this. Here is an object. It has mass. It's on Earth, so it's experiencing acceleration due to gravity, and it has some height. So they've graphed this out with bar graphs, and we see its potential energy is 10 at the very top. Let's just say it's 10. So their potential energy at the top is 10 joules, and since he's holding it at rest, kinetic energy would be equal to 0 joules. Here, it's half and half. So potential energy, I guess I should use the right symbol, is now 5 joules, and kinetic energy is equal to 5 joules. It's half and half. And down here, now this is the moment before it hits the floor. Excuse me. So its height would be 0, so its potential energy would be 0 joules, and its kinetic, all of its energy would be kinetic, or 10 joules. And so what we can say from this is that in the initial condition, there are 10 joules of energy, and in its final position, there are 10 joules of energy. So really, what we can say is the mechanical energy initial is equal to mechanical energy final. And that's an important concept. So mechanical energy initial is equal to mechanical energy final. It tells us that the energy in the system is conserved. And we can write that out long form. Kinetic energy initial plus potential energy initial will be equal to the kinetic energy final plus the potential energy final. We can write it out even longer form. Kinetic energy is 1/2 mv squared, so we could substitute those in as well. So now we could start to solve for unknown characteristics within here. So if I knew everything about its height and its mass, and I knew how fast it was going at the end, and what its height was at the end, I could solve for its initial velocity. Or if I know how fast an object is going at some vertical position and its mass, I could tell you how fast it's going at the end. So in short, this is one way for us to kind of avoid using kinematics to start to describe the velocity and motion characteristics of an object. Important thing to know here is this assumes no friction. So we know that if an object is sliding, there is such a thing as friction here on Earth, or anytime two surfaces are in contact, but that frictional force does work, and therefore it would change the energy into heat, and that would complicate our equation significantly. So as a result, we are always, when we talk about mechanical energy, we talk about what are called ideal systems. And in an ideal system, there is no friction. So in reality, energy is always conserved. When we consider friction, there's mechanical energy is converted into other forms that would be more difficult for us to account for. So we're always going to have to assume no friction or no air resistance. So just to kind of recap here, we've seen how kinetic energy and potential energy are related, and this would be total mechanical energy. And so now we have a change in kinetic energy, and we saw previously that work is a change in kinetic energy, is the change in kinetic energy. So now we can talk about energy being put in, right? So this person, to ride up this hill, has to do work. There is some distance, some displacement that they're doing, and in order for that to happen, they have to apply a force upward. And so when we have a force applied over some distance, we have work, and work equals the change in kinetic energy. So really, work, kinetic energy, and potential energy are all related. What causes that conversion from kinetic energy to potential energy and vice versa? It is the work that is being done. This would be the opposite, right? Work is still being done. The force of gravity, if this person's just coasting down, now there's a force of gravity that's causing them to go down, and they're going down that same displacement, so work would be done by gravity in this case. So it's important here to tie together mathematically that work is changing kinetic energy. Changing kinetic energy, that energy is going somewhere. That kinetic energy is becoming potential energy in an ideal system where we have no friction. So I hope this overview helps. There's also the text and some additional videos online as well to get your notes. And if you have any questions on this, please let me know.